temper is something that we thought will be nice to discuss in a professional society such as ISSS, because ISSS stands for mostly engineering efforts. And as I said, it's a conversation. So I would like to start by asking all of you to name some great engineers, since there are many people, and of course, many of you are engineers, or maybe all of you are engineers, and we have amidst us Professor V.K. Atre, an engineer a great engineer that I know personally. So if you start naming the things, it may be kind of difficult, but maybe you can type in the chat box. So if it is possible, or otherwise you can just unmute your microphone and say one by one. Let us say in different continents, different countries. So let's say in India. Let's start with that.
Sir, Mokshamundam Vishwesvaraya.
Yes, and after that, Vishwesvaraya was a great engineer from India. Any other names? Okay, how about from USA? United States of America, great engineers. Anyone can unmute and say it's. Let's keep it initially informal, so that we get the conversation started.
Eli Whitney.
Dr. Sridharan.
Sridharan also from India. E. Sridharan, the Metro Man.
Eli
From
Whitney.
the US.
Eli Whitney.
Eli Whitney, yes. Yeah.
Wright brothers.
Wright brothers are inventors more than engineers, but you can call them engineers, yes. Others? Okay. And from England?
Brunel.
Brunel. Isambard Brunel. Yeah, father and the son. That's good. And France? From France?
France.
Australia, Germany, Russia, great engineers.
Russia is a AK-47 inventor.
Okay, inventor, engineer, inventor. That's something that we need to discuss. Yes.
The man who invented AK-47.
Okay.
Kalashnikova.
Yeah.
Yes. Yeah. So usually, I've tried it in a few times in different forums. When you ask for great names who are engineers, usually the answers come much more slowly than if I were to ask, name some great scientists from any country. People would just, get the names out very quickly. So there is something that, we have when we say great engineers, we think about for a while and then start answering. Different countries, if you say scientists from any of these countries, you can give me a long list. Generally, scientists are better known than engineers. Great scientists better known than great engineers. And we wonder why. And usually, society recognizes, as we all know, scientific victories. Let's say we send a rocket into the space, newspaper headlines would say scientific victory. On the other hand, if the rocket launch is not successful or a bridge collapses, it's always engineering failure, engineering catastrophe, or people say technological disasters. Science is never blamed. Science is always given the credit, whereas engineering takes the blame when something bad happens. When something good happens, it's always science that is recognized. So if you want to be recognized by the society as a scientist, you have to discover something important, of course. As an engineer, the names that you have given, you gave Vishwesvaraya. If I ask, what is the great engineering accomplishment of Vishwesvaraya, you would probably say, what would you say? Vishwesvaraya's contribution as an engineer, great contribution.
Projects.
There are several. Yeah, the projects, big projects, right? He built the Krishna Sagar Dam and sandal factory and a lot of other things, but big things. If you just Sridharan, I already said Metro Man. He built the Konkan Railway and the metro and things like that. So an engineer to be recognized by the society, they have to do something monumental. A small discovery or something is not enough. Something that a scientist does sometimes alone is not what an engineer can do. Engineer needs a group, a team, a big dream, a big vision to create something big. Then we can say, like France, you didn't say Gustav Eiffel. Eiffel was a great engineer, right? But then we only know his tower more than him. We don't know much about, not many people know about what else Eiffel did. We only know. Sometimes engineers' contributions actually outshadow, they shadow the persons, right? So we say Tesla, for example, great engineer from the United States, right? We know what he did more than uh, what he was, right? On the other hand, technologists might not even be noticed. So there are different terms: a scientist, an engineer, and a technologist. So these terms are to be understood properly. They may not even be noticed, but fortunately, engineers and technologists make a lot more money than scientists, so they probably don't need recognition. On the lighter note, let's actually look at some semantics because there are different terms that we have. Let's say scientist. Who is a scientist? Everybody has a notion of a scientist. In fact, sometimes we call some people who are engineers and inventors and innovators, we call them scientists. But what does a scientist do? Scientist was a term that was coined as late as 1833. Until then, people were natural philosophers. The scientist is the one, according to William Whewell, who conducts scientific research to advance knowledge in a field. That everybody understands. What does an engineer do? It's much longer. So it's not easy to pinpoint what an engineer does. Here, for example, taken from Wikipedia here, who are practitioners of engineering. They're professionals. They would invent, design, analyze, build, and test machines, complex systems, structures, gadgets, materials, long list, to fulfill some objectives and requirements while considering the limitations imposed by practicality, regulation, safety, and cost. Right? Scientists simply need to advance the knowledge in a field, but engineers have to do a lot more. And and then we have this inventor or innovator. Actually, inventor is probably correct word here rather than innovator. The person who creates an invention. So sometimes when we ask for great engineers, names that come to us will be inventors. Inventors are different from engineers, and that's what I would like to discuss today, and actually seek your opinions also, because things are not crystal clear. If it were to be clear, there won't be this confusion that if I ask who are the great engineers, one wouldn't mention, for example, Alexander Graham Bell, because he was an inventor, or Thomas Edison was an inventor. Tesla was an inventor and an engineer. So there is a basically mix of all of these. And are these people not scientists? Don't they advance the knowledge in a field? That's another question, right? Because they do in their own way. But there is a distinction between scientists and engineers and inventors and innovators also. Let's look at these words. Scientists are usually associated with discovery. They find something new. So what is discovery? Discovery is an accident. Unexpectedly, you find something in the course of a search. So it comes from the Latin roots discoverere, which is cover, basically discover, uncover something. You find something that was hidden until then, you find it. That is discovery. What's an invention? Invention is to design or create something that did not exist. Engineers do that. Scientists find what is already there, that is discovery. Engineers design or create something that was not there. This is what Herbert Simon, who was a Nobel laureate, who said there is a science of the artificial. That's what engineers do. They are inventors also, for that matter. And then we also confuse sometimes the two terms invention and innovation. But invention is Latin roots in and venire, that is in to come. Something that was not there comes into being. That is invention. Innovation has different Latin roots. It's in nowhere. Basically, you make something new. Even in the Latin roots, there is similarity to invention and innovation. But innovation today is understood to be something where you make changes to a thing that's already there by introducing some new things. So scientists also can innovate, engineers can innovate, inventors can innovate. So it's actually something that's there, you make it better. Invention is like creating something new. But then there is confusion among these terms. As we go along and we discuss, maybe this can be cleared better. Now let's come to the word engineer. This engineer I've taken from etymology dictionary here. Again, it's a long thing. It's not as simple as what a scientist is, right? First, it says constructor of military engines. It comes from that engineer, the old English and 14th century. And the French engineer, architect, maker of engines, basically start from military. Initially, engineers were working for things that are required for war efforts. The late Latin is engineer, different spelling, inventor, designer. Here we have confusion again, right? So it goes on like this, wherever you look. And sometimes locomotive driver, when the steam engine started, locomotive driver was called an engineer. Today, we don't consider ourselves, drivers or mechanics. We are, when you say I'm a mechanical engineer, we have a different connotation of that. Maker of engines was called an engineer, right? So these are the things that we have confusion as to what engineer actually is. So sometimes even with our degrees, we have Bachelor of Engineering and Bachelor of Technology. So there is this confusion about engineering and technology also. So if I look at what is technology and who is a technologist, we have talked about who is an engineer, but there is confusion. Then now it also becomes this another issue of who is a technologist. A technologist is the one who implements technology. That's easy to say. But then what is technology? Technology is, people say it's a science of craft. It's more like a skill, something, process, method, techniques. That is something that a technology entails. And technology also has to ensure these things: utility, safety, usability, and finally economic viability. So engineering and technology, they're also slightly different. If I look at, again, from online Oxford Dictionary, it gives you the usage of the word, how many times. There is no ordinate here. I'm not saying number for the y-axis. X-axis is year, 1800. That's when engineering word started. Until then, it was more like a craft apprenticeship. Basically, if somebody is an engineer, they have to do apprentice under an established engineer and then learn all the techniques. That is still there with law and medicine today. You always have to learn from an expert. But we don't do that in engineering anymore. And you look at how the word engineering was used. It started there, 1800s, and then it went up and then reached a plateau uh, somewhere in the middle of 20th, just before that, early 20th century, and then raised again. There is a dip. We can't reason out why there is a dip. And then now it is again dipping and seems to be going up. I have this data till 2019, so it probably will go up. Look at technology. Technology started as a word much later, more like 1900s. And then it went up. That's also going down. Now, probably engineering and technology will be synchronous because both are now kind of considered equal. BE, BTech degrees are the same in a way that engineering technology are the same. So it's a more of a recent thing. And same thing with scientists also. 1833 was the first time people say the word scientist was used by Webel. Until then, it was natural philosophy. So these are not that old if you think about it. Now, let me just say my view on how do you distinguish among all of these things. A lot of terms: science, discovery, engineering, technology, invention, innovation, all of this. First, we know, because most of us are engaged in research. Research is a process of creating knowledge. That's what a scientist does. But creating knowledge is done by engineers as well as inventors and technologists. As students, we also learn. We are students forever, for that matter. Learning is the process of acquiring knowledge. One is creating, other is acquiring. So how does knowledge get created? So I've created a little diagram here. So knowledge can come from discoveries because you're advancing a field through a new finding. And if you are an inventor, if you invent something, then also you create new knowledge. And then this knowledge is fed to engineering. You take scientific discoveries and inventions and make them better. That's what we need to dwell a little bit more. And then engineers also create knowledge. And then out of this comes technology. And that's how I would view it. How do you distinguish? If you just take knowledge as the entity here, discovery, invention, and engineering, all of them create new knowledge. And all this knowledge through engineering, from discovery invention, funnels through the engineering and then becomes technology that we use. And what does technology do? We all know what technology, we use the technology every day. If you look at engineering structures, for example, I put a little cartoon here just to say that engineering is not all trial and error. This is Calvin and Hobbes. So seeing this sign, load limit 10 tons. So that's Calvin is asking his dad, how do they know the load limit on bridges? And dad being funny, he says they drive bigger and bigger trucks over the bridge until it breaks. And then they weigh the last truck and rebuild the bridge. That's funny. That trial and error thing is kind of made into a joke here. But that's not how engineering works. So inventors may try something just with their flash of idea. Scientists will go systematically to find things. But engineer takes both of these and works on it. So when they put load limit 10 tons, a lot of engineering would have gone into this bridge. I would say there are three modes of research, again, to dwell on these terms. There is observation. You do experiments or you just observe nature and things around you and try to understand. And then there is contemplation, thinking. You think about why the things the way they are, or how can things be better? You contemplate. And then there is implementation. You build things. So if I take these three as the modes of research and try to understand what a scientist does, what an engineer does, and what a technology does, what an inventor does. Let's say scientist. Scientist normally starts with observation. They do experiments, they observe things. They do their own experiments or just observe the way things are. They may look at rocks and find things about it. Or they may devise an experiment to understand what rocks are made of or how old they are and things like that. It always starts an observation. And then they analyze, that is a contemplation. And eventually they may actually go and implement it. An engineer, on the other hand, I would argue, they start with contemplation, analysis. They try to understand because they sit on top of physics and chemistry and other things, which are basic sciences and mathematics. We try to analyze. So we don't just observe, we just analyze and then see how can I make it better? How can I create something new? And then they would implement. And then finally, they might even make some observations about things and go into the realm of science. An inventor will just, Edison comes up with the idea of an electric bulb and then just makes the bulb. Graham Bell, just makes a telephone, right? They don't worry about the nuances of the theory underlying it. They just want to implement and then show that it works. It's an entirely different trait that inventor has. After that, they may make observations and then they may do analysis also. So these three things, like in a cyclical pattern, so we could actually put along a circle. If I take research as a full circle, there could be part of it, I just put 1/3 for each of them, but it could be any proportion, depends on the topic of research, observation, contemplation, and implementation. I would say an engineer starts in the contemplative region, analysis. Doesn't need to start here, somewhere here, and then traverses this thing. Whereas a scientist would start with observation. Generally, I'm generalizing here, so not a specific thing. There could be exceptions. An inventor would start here, just readily implement an idea without having to analyze it or observe or hypothesize anything, just making and showing. So if we do that, if somebody does all three, for example, they start somewhere and then go the full circle wherever they start. They can start here and come back here. They start here and come back there and start here and come back here. Full. They are in a way complete researchers. Are there examples of complete researchers who can be characterized as a scientist, an engineer, and an inventor? there are. I would like to mention a few examples today. And where is technology here? Technology, I put a circle outside. So any of these, scientists' observation can actually create technology, and there are many examples. And engineers, of course, create technology. Inventors also create technology. So technology takes from scientists, engineers, and inventors. And like I said earlier, innovators, everybody's an innovator. Whoever makes something, embellishes an existing idea, existing technique, existing process, existing method is an innovator. But I'm focusing here on scientists, engineers, and inventors. And technologists will be all of these. They take from here and they make things. And they have to really be the practical people at the end. Sometimes we have this engineering science that gets even more confusing. So there is engineering and science, which are distinct way of looking at things. And then we have engineering science. So technology, all these things, I would say, fit together in this manner. It could be debatable. That's why I said it's a conversation. So we'll have questions later. So let me complete my picture. So knowledge, discovery, invention, engineering, out of that flows technology. Technology is the one that gives us the products and services that improve the quality of life. And we also can think about engineering discipline. For every engineering discipline, there'll be underlying science discipline. If I say mechanical engineer, there is physics. If I say chemical engineering, there is chemistry, right? For every engineering discipline, there'll be underlying science. They're intricately related to each other. Now, let me come to the topic, the temper that I put in the title, engineering temper. Etymology of temper. It's Latin root, mingle, restrain, temperare, and temperian, Old English, bring something into the required condition by mixing with something else. And the Old French temper, it's moderate. Basically, what temper means is a state of mind. It's a mood. So actually, you say, I'm in a bad temper today. I'm in a bad mood. That means that my way of thinking is different today. I'm in a happy mood, right? So this habitual way of thinking, behaving, and acting, that is a temper. I would like to talk about the engineering temper, but before that, let me actually talk about scientific temper, which is a word that is often used. It's a way of life. Wikipedia says scientific temper is a way of life which uses a scientific method and which may consequently include questioning why, what, where, observing physical reality. Observing is a scientific trait. Testing a hypothesis, analyzing is also part of it in a later stage after you do this. And communicating before writing the paper, not necessarily in that order, it says. That's scientific temper. It's a way of life, it says. Actually, when I looked up scientific temper, I came across this. In fact, the Wikipedia page also credits Jawaharlal Nehru in his The Discovery of India book. There's a passage from there. He used this temper of science, scientific temper, temper of science. He says the applications of science are inevitable and unavoidable, but something more than its application is necessary. The scientific approach, the adventurous yet critical temper of science, the search for truth and new knowledge, the refusal to accept anything without testing and trial, the capacity to change previous conclusions in the face of new evidence, the reliance on an observed fact and not preconceived theory. And this should be a way of life. He also says that it's a way of life, a process of thinking, method of acting and associating with our fellow men. I guess now we'd say fellow women and everything. It is the temper of a free man and woman. We live in the scientific age, so we are told, but there is little evidence he worries about it. We can still worry about that. Scientific temper not being enough in people. He talks about leaders, but it's a nice passage. And in fact, there is another one that he continues in the same chapter, The Discovery of India. Science deals with the domain of positive knowledge, but the temper, that's where he explains it's more than science, he says. The temper which should produce, the science should produce a scientific temper which goes beyond the domain. He gives an interesting example. If you look at a botanist or a zoologist, they may never experience the charm of beauty of nature, he says. In a similar way, a sociologist, a social scientist, may be wholly lacking in love for humanity, contrary to what you think they might do. On the other hand, he says, when we go to the regions beyond the reach of the scientific method and visit the mountain tops where philosophy dwells and high emotions fill us, or gaze at the immensity beyond, that approach and temper are still necessary. So Nehru here is differentiating science and the scientific temper. Scientific temper, as we understand, is a trait, is a way of thinking, a way of behaving, and a way of acting. So I was actually reminded when I was thinking about scientific temper, this scene from the movie. Can anybody say which movie this is? You see Shah Rukh Khan there. You can unmute your mic and ask, say.
Swadesh, sir.
Yes, Swadesh. And it's a fantastic scene where to villages, kids and everybody, there'll be a movie being shown, maybe Amitabh Bachchan's. Everybody's excited and the power goes off and everybody is disappointed. Then Shah Rukh Khan just gets up and takes his telescope and points to the night sky and then engages everybody. It's actually a scene that gives you goosebumps. Scientific temper in our daily life, way of thinking. The moment you look at the night sky, look at the stars, you wonder what they are, right? That twinkle, twinkle, little star. That is scientific temper. So conveyed in a Bollywood movie, right? But now, what is the engineering temper? So I typed engineering temper in Google. What I get is metallurgical tempering. And if we go down few more things, I get 20, 30 engineering temper if I do in Google. It's all about tempering, metallurgy, and heat treatment. So interestingly today, engineering temper as a phrase is not available in the internet or in the lingo. So if scientific temper is to look at everything and questioning why, what, where, all this reasoning that Nehru so eloquently talked about, and we all hear this scientific temper, then what is engineering temper? So what do engineers do? We all know we're all engineers. We create things. We improve understanding of a concept. Most of the time, more than creation, we improve understanding of a concept. We use science to solve problems. And we probably sometimes perfect a technique also, which is different from technology. Technology has to produce things economically, safely, and so forth. Engineering is in between science and technology. For example, when Ørsted, this is Ørsted here, Hans Christian Ørsted, when he said that by passing electric current in a coil, you create a magnetic field. If you think of using that science to create electric bell, then you're an engineer. You could be an inventor, but engineer. But then inventor can get the idea, okay, I can make an electric bell. But then you have to do some calculations. Just like the bridge I showed, it's not like I think of, okay, this shape of the bridge. Actually, I think of the strength of the bridge and stability and lots of things, which material to use, what dimensions, everything I have to think of. In a similar way, even if I get an idea of making electric bell after knowing Ørsted's discovery of linking electric field and magnetic field, I still need to worry about how much current to put, what battery do I put, how much current will be there, what is the resistance, how many turns, and how much force would it generate? Is it enough for the spring here to come back and ring repeatedly, right? Similarly, this is Tesla, Nikola Tesla, one of the greatest engineers of the past. After knowing electromagnetism and everything, to create motors and power supply and everything that he did, hydroelectric projects, a lot of engineering, lot of modeling, lot of theory. So engineering is a lot of details. It is not just one simple finding or ultimately technology. In the gap here, we have to do a lot of modeling, a lot of trying out various things, analysis. For example, if you take lasers, laser, you can say, since it won Nobel Prize, we can call it a discovery or science. It was done by a physicist, actually few physicists. There are two Russian physicists and an American physicist. That's science, laser amplification by stimulate emission of radiation. But once that is there, that's not enough. That's not going to give us all the applications. With just discovery there, I'm not going to get a laser pointer or a laser machine, a laser eyes surgery, or a laser show display that we have. All that applications or technology just cannot come from here to here. In between, there is a layer of engineering. The laser, what wavelength, what intensity, is it a pulse laser or some other laser? Now we have femtosecond lasers that are used. all of this is a lot of engineering goes in there. You take something from the science, you use this concept, a discovery, and before it becomes technology, a lot of engineering is there. And then what is a temper? We understand what engineering is now. What is the engineering temper? Before I talk about a few great engineers, here is one. Actually, he was a professor at the University of Melbourne in the 19th century, Charles Carnot. And he was one of the early engineering professors in Australia. Australia was not far behind England after the Industrial Revolution. They were only maybe a decade or sometimes even less than a decade in implementing everything. So he had said this something very interesting. So theory and experience are of equal importance to the engineer. He was teaching, actually making engineering curriculum and teaching people. Uh, Theory and experience both are important, he says. Theory without experience is a foundation without the superstructure, and experience without theory is a superstructure without the foundation. The play of words. One is experience is the foundation without a superstructure, if you have theory, and experience without theory is superstructure without foundation. The former is useless, the latter is dangerous. This actually summarizes what engineering is in some sense. Engineers have to learn the theory, they have to master the theory, and then go beyond it to apply it, to create new things and perfect things. Whereas inventors don't have to do all that. They just have an idea, they just build it and see if it works. Otherwise, they'll use ingenuity to it. Whereas engineering is a lot of details. Now, I would like to talk about a few famous engineers. Then actually it'll become easier for me to make my arguments about what the details are, what the engineering temper is, what was there in these people. Maybe you recognize some of these people. This is James Watt, one of the greatest engineers. And here is actually, I put Maxwell. Maxwell is a physicist. He's a great scientist. He was a great scientist. But I want to show an engineer in him. He had that engineering temper. And of course, this is third one is Gustave Eiffel, great French engineer. This is A.G.M. Mitchell, great Australian engineer, who was a student of this Carnot that I just talked about. And here is Bucky Filler. He was an inventor, but he had that engineering temper. And I'll show examples of what these people have done that we can understand the engineering temper. So Eiffel, let me start with Eiffel. There's no particular order. Eiffel Tower, if you look at it today, it's a very beautiful structure, we say, but more than beauty, it has optimality written all over it. If you look at these cross beams, those cross beams have cross beams, and those cross beams, if you take one of them, that has cross beams. There is a hierarchical thing, which is what the natural materials have. If you look at Havershell Canal in the compact bone, you have basically at the molecular level, collagen molecules, a triple helix structure, and then there is collagen fibrils, becomes fibers, and they become lamellar arrangements to this. This type of thing Eiffel had done. He was a chemical engineer by training, but his understanding of mechanics and structures was really marvelous. I've read his biographies, I say, 2 or 3. Yet I don't know how he came up with these things. And this real Eiffel Tower, you can see the cross beams, and cross beams. And this was there in many bridges and other structures that he had built. This is Maria Pia Bridge in Portugal that Eiffel had built. And this cross beams within cross beams becomes a hallmark of Eiffel. Today we call them lattice structures, and we are using a lot of mathematical techniques to arrive at these designs. But he had somehow gotten that engineering spirit to use material economically, and materials also. When everybody was using cast iron and other things, use wrought iron to build bridges and towers, which kind of did not exist of such magnitude before his time. They were using concrete and other materials, but he had used this. And his hallmark of this hierarchical design is so influential that we can find it in Howrah Bridge also. We have these cross beams at one level, not at 3 levels that Eiffel had done in his tower and bridges. We at least see one level. And anywhere you see, next time you look at a structure, you see that people don't make solid things. They make them porous, and that's what we are trying to do with additive manufacturing today. My student Meenakshi Sundaram and I wrote an article some time ago about Eiffel's optimal structures. Those are interested can read Resonance and find out about Eiffel's greatness. And there is actually aesthetics also an engineer worries about. Scientists worry about aesthetics in a different way. It's more abstract. That engineers can create the Eiffel Tower. This is something that it's called pointillism. George Seurat, a painter, he just puts dots here and there and creates a painting. And somebody compared Eiffel's designs like that. You have little things here and there. The sum of all of this is very beautiful and economical and optimal. And I would like to now talking about structures, an engineer that existed in Maxwell. So Maxwell had this amazing paper, which we are reading as people who work on structural optimization, that he talked about reciprocal figures, frames, and diagrams of forces. Why did he have to worry about mechanics? Because he was doing, all his electromagnetism and other experiments and theory and modeling, but then he had to make his instruments. So he had that scientific temper as well as the engineering temper to see that, can I actually do this? Why are things where they are? So it probably took a little bit of time of Maxwell to do this, but it's a very detailed paper and people are still using his concepts. For example, what you see here is another great engineer, I would say, or architect. This is William Baker, who did this Burj Dubai and a lot of other things. He's there now in Chicago with his firm, and he's using, and so do we, Maxwell's things by what he talked about. If you have a truss, this is the truss. That's what's called a form diagram, and it is dividing the entire space. So you have E, A, B, C, D. Wherever the forces are, I divide this space into A this side, B that side, and so forth. And then when I put truss element, there is region 1, 2, 3, 4, 5, 6. This is the form diagram, the way the truss looks like. This is what Maxwell had done. This is a force diagram because every truss element will have a force in it. So between 1 and 2, each region becomes a node here. It's a complementary, a dual here, reciprocal diagram as Maxwell had called it. One becomes what is a region here, what's called interval space, becomes a node here. Likewise, this A becomes a node here. And what joins 1 and A here is the force in this. This horizontal force will be in that direction. So this is a force diagram. So we created this form diagram and reciprocal force diagram, Maxwell. Now this architect, William Baker, is using it to create optimal structures. When you have this dual force and form diagrams, and there is another little thing that Maxwell had done, which is to say that when you have this form diagram and force diagram, you start moving these nodes. Okay, let me go to previous thing. If I start moving, I have three forces that I need to hold economically using the least amount of material. How do I connect? That's topology. I can connect like this, or simply connect these three vertices to make a triangle, right? But then there are other ways. If you do, you get more optimal structure. So what Maxwell had said was, if you look at the form diagram and force diagram, the lengths in a form diagram indicate the lengths of each truss member, and a form diagram indicates the force in it. He said, you multiply the length and the corresponding force and take the sum of all of these things. If you minimize that, that will give you the least weight structure, optimal structure. The force and the length, if you multiply, that is the nature of fully stressed design. Every truss element has the same stress. So we can replace the area by, because the force divided by area is stress. If stress is constant, you can replace the area with force. And that's when you get this. Using that principle, he had designed structures, Maxwell. Now we are using it today and putting mathematics for it. Now, this is a force diagram, this is form diagram. Both are identical, self-reciprocal. Then it is a special kind of a truss. So you can have this truss, this identical, and that's optimal one. This was done by another great engineer, who was an Australian engineer. This paper is written in 1904. It's called using this Maxwell's theorem that I just said. Sum of all the forces multiplied by elements in all the elements. If that is minimized, you get the least thing. That's what you use. He starts with Maxwell has shown. This is the formula, right? Of course, it's a minus sign because there will be compression forces in some members, tensile for others. Using this theorem, Michel came up with optimal arrangement of these structures. And today we use a lot of mathematics, homogenization and other things, Kuntakar conditions, all of the maths. We come up with what they had sketched with their engineering temper, I would say, engineering prowess. We get that with our optimization techniques. And this is more of mathematics, but what AGM Mitchell had done based on Maxwell's engineering theorem, we get the designs that are same as what they have done. So they didn't know the mathematics, but they had this engineering way of thinking. And now let me turn to another great engineer, James Watt. James Watt has done many things. We associated him with normally steam engines. He didn't invent it, but he perfected it. So before that, Newcomen's water pumping, now that first industrial revolution, needed for coal mines, how to get water out of the mines. They were doing this water pumping for steam engines. And the piston has to move along a straight line. And people were trying a lot of things. So this is the problem that was faced by James Watt also. He came up with what is called a straight line linkage. So basically 4-bar linkage. You see 3 bars and the frame is a 4th bar. And the middle bar, what is called a coupler, as these things rotate about point C and point D, these cranks as we call them, a point F here actually traces a nearly straight line for a portion of its traversal. This was actually what James Watt did. And this is not easy. You cannot do that with just thinking in your mind. You have to work out the mathematics. And he made the straight line linkage and improved the performance of steam engines a lot. And that's what an engineer does. And he had variety of things, not just this, variety of mechanisms that he did. Planetary gears connected here, and then you would turn the reciprocating motion of a piston cylinder somewhere to continuous motion. So what we have now, piston crank engine, the early roots were laid by James Watt. Of course, his centrifugal governor, it's a marvelous feedback system. To control the speed of it, he put this thing that turns, and that would make again the linkage. He was a specialist in linkages that would move, uncovering a hole to release the steam and slow down. And then it will pick up the speed again. Very nice closed loop system. There is no sensor specifically, there is no actuator specifically. You are using the system itself to do it. And these are the kind of things that we want. Mitchell also had made thrust bearings with a tilting pad. The Australian engineer Mitchell I showed, he has also done. This is the marvelous engineering they have done. In fact, James Watt, towards the end of his life, he had actually made things. If you put a 3D replica of something, is more like a sewing machine. If you put your foot here and then do back and forth motion, it would actually make a replica of that. Very sophisticated one. I've seen it in the London Museum, where there's a entire James Watt's workshop or a lab is actually recreated and put there. Marvelous, great engineer. But it was actually very interesting that there was a scientist in James Watt. And this is what we have. I did an article with my student Sangamesh Deepak, some time ago in Resonance Again. I'm fascinated by engineers, great engineers. Archibald Barr, who was Optical Society president at the time, he said of James Watt brought to bear on the practice of mechanical engineering a mind trained to consider scientifically the problems that presented themselves in his practice. So he was a scientist. In fact, James Watt was one of the first ones, or maybe the first one, to suspect that water is a compound and not an element. It was not known James Watt's time whether water is a compound element. He had apprenticed at that time. Engineering was always apprenticeship in Joseph Black's chemistry lab, and he had learned all these, and he had actually suspected that water is a compound, and that's actually remarkable. And you can actually find some of the scientists citing James Watt's work. We know James Watt as an inventor and engineer. There was a scientist in him. He was one of those people who were a complete researcher. And next, I want to talk about Buckminster Fuller. He was an inventor, but then he had this engineering temperament. And this is a very interesting story that when he was a child in kindergarten, the teacher used to give apparently dried peas. You take green peas, the peas that we eat, green peas, and when they're green and raw, you take a toothpick and make some indentations in it. And then when it dries, that becomes a hole. The whole indentation remains as a hole. Then you can use a toothpick because now it would have uh, contracted a little bit by losing water. Now if you put a toothpick, it will hold it. It's like a more Lego blocks. So there somebody had invented this technique to go to kindergarten people to make them make structures, because normally an engineer today for us is Lego blocks, right? Something they build an engineering structure. So when Buckminster Fuller was a kindergarten student, and everybody was given toothpicks, and everybody was making more like cubes or parallelepipeds, but this little kid, Buckminster Fuller, made something today is known as octet. It's a tetrahedron and octahedron combination. It's one of the optimal structures to make these lattice structures. And the teacher noticed this Fuller and then said, this guy is remarkable. And then he was working on what times he actually made how to reduce the effort when you are rowing. He put actually a conical thing that can deflect and like invert an umbrella to do this, and many other things. So right from the beginning, throughout his life, if you read his biography, you actually see that when he was working for a construction company, he had these bricks that he made with holes. Today we have breathing bricks. He had done that. And not only that, he actually thought that the concrete could be poured into these holes so that you don't need mortar to construct these things. Whatever he did, he tried to think of a new way of doing. Did anybody recognize what this is? What map is this?
World map.
World map. Good. You saw the pattern. So you probably know what to talk about, right? So this world map he had done. See, normally whenever you do the world map, so what they call this cartography projection, it is always a distortion because the poles and the equator have the same width. So everything looks very distorted. But actually, if you were to project the Earth or the globe onto icosahedron, which has 20 equilateral triangles, and then develop it, the map looks like this. This is called actually DYMAXION map. So Fuller was a DYMAXION man. It's a DYMAXION word also was coined for him. It's a dynamic maximum, meaning optimum, ion, ION, to indicate there is some scientific thing there. DYMAXION, he did that, and he made a world map which is least distorted. And that's actually amazing. It looks like an island actually, if you look at it, but it's a world map projection with this DYMAXION projection. He also asked other question. This is the engineer's mind, engineering temper that he had. He would ask, if you were to go into space and look at Earth, which point, if you are right above, you would see the most land mass. Okay, today you can go to Google Earth, keep rotating it, which I did to create these two. So if you keep rotating, you have to be, let's say one day we're all going to space, maybe, as travelers. From space, you want to be right above a location on Earth where you see the most land mass. Okay, he asked that question, and he says, if you are French Riviera, right above it, you would see the most land mass. Similarly, you can also go to other place where there is most water will be seen in this circular projection that you have. So French Riviera is somewhere there. He thought that if you're right above it, you would see the most land mass. But he didn't stop there, because he had the right projection of the world map. Now he would actually put energy grid, what he called DYMAXION projection of the world map. Now if he says energy grid is like this, that will have the least wastage. So whatever he did, he came up with this idea, how can I make things around me better? And he had created DYMAXION car, a DYMAXION house, even a DYMAXION toilet, where he said everything should be optimal. Nothing was insignificant for him. Of course, he's known for his Fullerene tensegrity that I'm not going to talk about. Everybody knows. But here was a man, he's called a DYMAXION man, dynamic maximum, optimum ion, the word that somebody coined for him, a wordsmith. He saw this engineering temperament in everything that he did. And I've written an article about him also in Resonance. Those of you interested, you can read that. Amazing, what engineering they did. Now, let me just conclude to say that if looking through the telescope or just looking at the night sky is a scientific temper, that's something that we have to have in everything we do. When you learn about electric field, magnetic field with a coil, immediately you should think about, I want to make electric bell. And I need to know what resistance the wire I should have, and what current it will have, what battery should, how long it will last, and how much force will generate, all of that, right? These are scientific temper. Then what is the engineering temper? Just with this, looking at the stars, I would say this young man, Awais Ahmad, he gave a talk just before the lockdown in 2020 February in our mechanical engineering department. He's just 24 at the time, and he has this company called, the CEO of the company called Pixel. If looking at the stars and wondering about his scientific temper, engineering temper is what, for example, he is doing, what he calls seeing the unseen. Pixel is on a mission to build a monitor for the planet through a constellation of cutting-edge hyperspectral small satellites. His company is actually putting a constellation of small satellites in the orbit, which will be observing not optically, so he says hyperspectral, several wavelengths, and looking at what he says unseen. This is what engineering temper is. Scientific temper is wondering what the stars are, where they are, how old they are, but engineering temper is actually putting a few stars up there, or at least satellites. So thank you for attention. I'll be happy to take questions and learn from you what you think is engineering temper. Thank you.
Thank you very much, sir, for a very interesting talk. And the floor is now open for question answer. Please unmute yourself and ask question, or you can write it in the comment box.
Dr. Suresh,
Yes.
your talk reminded me of a great book which was there in a Russian publication, if you remember, Design of Mechanisms in 7 volumes.
Yes.
Which had exactly the links and the kind of structural. Yeah, Artobolevsky. Could IISc, your department, think of republishing it, because there has been no other book of that type, and your talk almost deals with nice aspects of that book. It is a very nice talk.
Yeah, thank you very much. Artobolevsky's volumes are there. There are also Jones volumes are there, UK person, and then Chironis has a modern atlas of mechanisms, linkages and things like that. Yes, they have been, and these are also digitized and they're available.
Thank you.
Yeah. Also, Franz Rolla, another great French engineer, he had actually physical models of all of these. Artobolevsky also had physical models are there. Those collections are there in Cornell University, and they're all digitized now. Actually, they're available.
Thank you.
There is a question, sir, in the comment box. Somebody is mentioning about the MEMS is a failure from industrial point of view. Do you have any comment to give on it?
What's that, MEMS?
In India, MEMS is failure from industrial point of view.
Oh,
any
failure.
Comment? Yeah.
Failure. Oh, no, certainly not. Certainly not. Actually, MEMS is something ISSS can actually take credit, and Professor Atre and others are here. So actually, MEMS is a kind of a household word today in engineering colleges, and a lot of things are being done. I think in terms of, you may be asking about having companies making MEMS devices in India.
Right.
That also will happen. I think it's a matter of time. So I don't think it's a failure, but there is a lot of engineering there in MEMS and nanotechnology and everything now, MEMS, NEMS, whatever. So they're all, I think, there are courses are there in MEMS in many colleges. So certainly not a failure. I think it will definitely, thrive more and more as days go by.
I just want to make a comment, Anand.
Yeah.
I had an opportunity to listen to Morgenstern once, John von Neumann and Morgenstern thing. And he had come to the university where I was a student, and he gave a talk and was trying to distinguish between a physicist, mathematician, and an engineer. And he gave an example. He said he was standing, three people of these physicists, mathematics, engineers are studying on one side of the Tiber in Rome. On the other side, they saw a beautiful girl walking. And the engineer, physicist immediately said how to build something, rocket, and going on to reach her. And where the mathematician was doing it the optimal way of reaching her as fast. And by the time they finished the calculation, this engineer had swum across the river and gone away with the girl.
Yes, that's a nice way of putting. Yeah.
Yeah, Morgenstern was talking about theories are good, calculations are important, but can they be implementable?
Right.
Can you do something to implement it? And then he goes on to say what engineers design finally need not necessarily be optimal. And need not necessarily be fully scientific in the sense everything has been analyzed and it, but it works. So something which meant to work of a thing which didn't exist, he said he called it engineer.
Right. Yes.
So I thought I would even people like Morgenstern had this concept of engineering as something which can be implementable.
Yes.
And obviously innovation is involved in some sense.
Right. Yeah. Yes.
Thank you.
Thank you, sir.
So Suresh, one maybe your thoughts on, one of the other great physicists who had an uncanny engineering sense and innovation, invention is, I think, Richard Feynman.
Yes. Yes.
Because he invented his own techniques in calculus when he was a young student.
Yes.
He invented several devices in the Manhattan Project, which are sheer engineering.
Right.
And again, when he did the Challenger disaster analysis, it was sheer engineering sense. So I think he's another great example of a physicist, an engineer, and an inventor, innovator.
Yes. Yeah, it's actually funny that you mentioned actually, I think Feynman had used even pick locks, right? So all those wonderful things he did. But also
absolutely.
when he did this Challenger disaster investigation, he had this famous line, physics cannot be wrong. Because whatever went on wrong was actually engineering judgment, right?
Yeah.
So that was also a famous line that he had. Physics cannot go wrong, right? He even had a little demonstration of what had happened, and then later when somebody asked him, this is what that Madhu Atre told me, that when somebody asked, did you know that it would work? He said, well, I said, physics doesn't go wrong, is true, but engineering can go wrong sometimes.
So I have one question.
Yes.
Don't you think that system engineering is a part of somewhere it should come into the domains that you talked about, but consciously you didn't mention specifically.
Yeah.
I was just going to ask you, because engineers necessarily don't discover any new things, but they try to utilize the laws and concepts that is available in the state of the art, but they synthesize new products, and essentially system engineering concepts has to be involved in this.
Yes, true. I think that's very much true, because engineers always look at the whole thing, because they have to make something work, right? They have to look at the whole thing. So systems engineering is definitely should be a part. In fact, that is not taught in the engineering curriculum at undergraduate level so much. We only teach them applied science in some sense, right? We teach them, let's say, mechanical engineering, we teach them fluid mechanics, solid mechanics, heat transfer, thermodynamics, but systems engineering of building things is kind of eroding. This is something that people had worried about long time ago. We still worry about it. So I don't think the engineering temper is taught to the engineering graduates. I don't think after 4 years they feel that I'm an engineer, I can create things, I can build things. That confidence probably is not there like a doctor has, for example. Some people argue even a physics after masters or PhD also, they may not feel like they are actually a scientist. That's also there.
But with the evolving of new technologies in the coming decades, I think system engineering is is going to be an important area where unless you master that area, you cannot create new products.
I agree. Yes.
I want to share some thoughts here. Yesterday,
Yes.
I was trying to inaugurate an exhibition of one of the engineering colleges in northern Karnataka, where there is a system design course in the first year of engineering. So all the students were given a problem. For example, there were clearly some problems on COVID. How do you build a mask for a system? Or somebody said that what would be called as a mundane, you want a biscuit thing, how do you do it, and so on.